Hello and welcome to another video. In this problem, we're going to be working on palindrome rearrangement queries. And this is going to be the last problem of the weekly contest 378, and it's quite a tough one to be honest. So in the problem, you're given a zero-indexed string s having an even length, and you're given a query where you have a query with a, b, c, d. And for each query, you're allowed to perform the following operations. Rearrange the characters within substring SAB, and rearrange the characters within substring SCD. And for each query, your task is to determine if it's possible to make S a palindrome by performing the operations for each query answered independently of the others. Return zero indexed array answer, where answer equals true if it's possible to do it, and to make it a palindrome after making these rearrangements, and false if not. So a substring is a contiguous sequence of characters within a string. S, X, Y represents substring consisting of characters from the index X to the index Y, both inclusive. So in the first example, you're given ABC, ABC, and your first query is 1, 1, and 3, 5. So you can change B and C around, and you can also change A, B, C around. So this is possible. There's a bunch of ways to make this palindromic, but basically, because you have the same characters on the left and the same characters on the right, you don't even need to change these two, because you can change the whole right side. You can just make it match, right? So you can just say ABC, and then for this last part, ABC, you can just turn it into CBA. And that would be like one way to make it match. There's a bunch of different ways. Okay. And in the second one, you're allowed to change the entire first left side, and you can change the last letter. So once again, because you can change the whole left side, you can just make the left side palindromic with the right. So if the right's ABC, you don't need to change that. You can just make the left palindromic with that, so you can make it like this. And that would be palindromic. So both of these should return true, and they do. So in the second one, you kind of don't even need to know like what the query is. This is never possible, because if you just divide it in half like this, the letters on the left and right aren't the same, right? So it's not possible to make this palindromic, because any query where the letters on the left half and the right half aren't the same, like you have to have an equal count of each letter, it's not possible to do it, right? Because there's a D on the left, E on the right, so like no matter how you rearrange, it's never going to be possible. And in the last one, we have this ABC, ABC again, these three letters that are the same. So we're allowed to change C and B if we want to, and we are allowed to change A and B. So this one is possible, so we can change, like, we can change these two like this, and then this A and B, we just want to switch to make it like this. And that would be possible. So let's break it down into a few parts, and let's also look at the constraints, which is kind of important. So you have 10 to the 5th characters in S, and you have 10 to the 5th queries. Each query has four letters and so on, and A and B are going to be in the left half, and C and D are going to be in the right half of the string. So we need something like, we need to be able to perform the queries in n or n log n or something like that, right? Because we basically need to be able to perform them, or sorry, we need to perform each query in either constant time or log n time to be able to pass this, because there's 10 to the 5th queries. So typically when you have this, when you have the constraint on queries is really high, you want to be able to do some pre-computing, and you want to be able to pre-compute something, and then that way you can solve your queries really quickly, right? Because otherwise you're going to be doing repeated work, and it's gonna fail. So the first thing is something like I mentioned before. So if we have some characters, like let's just say this is the left side of the word, this is the right side of the word, something like this, right? Like we're always gonna have even length words. So the first thing we can do is we can just check, is the character count here and here equal? Like every single character has the same count in order to make it a palindrome. If not, we can just return false for every query right away, because this will never work, right? Like there's no rearranging you can do. For a palindrome, you have to have the same letters. So that's pretty straightforward. You can just make a counter on the left, counter on the right, compare to the C, they're equal. Now the other thing that I will do for the word is I will actually make it a little bit easier, and I will change C and D just to make it like easier to be able to do stuff on it. So let's say our word is like this. So this side does have to equal this side, but it has to equal in reverse order, right? So if this is like 0, 1, 2, this is 3, 4, 5. So 0 has to equal 5, 1 has to equal 4, 2 has to equal 3. So what I will do is make two words. One will be this word over here, right? This left one. And the right one, I will take the right half and just reverse it, right? And then we can figure out C and D based on the indices. So for example, our two words will be like left will be ABC, right will be ABC, both with just like normal indexing. And now this 5 index will be the index 0 of the new word. That's pretty straightforward how to convert those, right? Like let's say this was C and D. You can just take the index of the last character in the right side, subtract D to get the new D index, right? So D, actually, it would be a little bit different, right? So if this was C and D, basically I'm just gonna remake C and D to make this match. So C and D need to be the first and second character, but I'm gonna make it in the opposite order because it really doesn't matter. So what's gonna end up happening is like this is, let's say A and B is over here or whatever it is, doesn't really matter, maybe over here. I'm going to make C and D these two characters now. Because it's still the same range that I'm flipping, right? So it doesn't matter that like I reverse C and D, like that part doesn't matter at all. So that's what I'm going to do. So just reverse the second half and make C and D the same range, but put them on the other side. So instead of this being D, I'll just make it C instead because it doesn't really matter. So, and like I said, you could do that. So you don't even have to make a counter here if you don't want to. You can just split it, and then and then you still have to make a counter because you do have to make sure that like the counts of every character is equal. So now that that's the case, let's look at, and we'll look at it in both of these. Let's look at what would happen, like what are all the different cases we can run into. And actually, what I'm going to do is I'm just going to use two arrays. I'm not even going to have the characters. Let's use two indexed arrays. I'm not even going to have all the characters. I'll just add characters when I need to explain all the different situations. So let's pretend this array is this left half, and let's pretend this array is the right half, right? And let's just pretend like this. I'm not going to fill in characters yet until we make certain examples, and then I'll fill in characters for those examples. So there are, like, your queries can interact in a few different ways. And let's go over all of those ways. So for one thing, one query can completely cover another query. Like let's say my A and B is here, right, for this word, 3, even 5. And then when I rearrange this right side, my C and D are over here. So that means that these characters completely cover these characters, right? So because I'm allowed to flip all of these characters, I don't really care about this. I just need to make sure that a couple things happen. That the character count here and here is the same. So let's actually write this down for like our type of queries, right? So first query, one query, or like one, let's call it half, covers the other. Right? So for this to be palindromic, we need a couple things. We need a bigger half to have same character count as smaller half in the query, obviously. And then we also need the left and right side that isn't in query to be palindromic. So what I mean by this is we can fill in some characters now just to make it a little bit clearer. So let's say here we just have some characters like A, B, C, D, E, F. And here we have the same characters, but they are in some other order. Let's just say maybe like F, B, A, C, D, E. So because we can rearrange this whole thing, we can have it match this, right? And remember, this is reversed. So in order for this to be palindromic, these two strings have to be exactly the same, right? So if I have something like A, B, C, C, B, A, when I reverse this section, A, B, C will equal A, B, C. So in all of our examples, this left will have to match the right exactly, right? And so it's always going to be possible to make this section match this section if I can rearrange everything in this part, right? Because CD covers AB, that's why I don't really care. I don't even have to like do anything here. I can leave it whatever it is, and I can always rearrange these characters as long as the count of every character is the same. right? It's like if you have a palindrome, or if you have a palindrome with like a bunch of letters, let's just say I have like A, B, C, D, E, and then I have some letters here. I have like in any order I want, like this, let's say. If I'm allowed to flip all of these letters into any order I want, I'm always going to be able to make it palindromic, right? I can always just do this. So that's kind of the same idea here. If you can flip all of them, you can always make it palindromic. You just have to make sure that the count here is the count here. But because we have to be able to do our queries in nlog n or O of n, or sorry, we have to be able to do our queries in log n or O of 1, we can't just like count up this whole range, because this whole range can be like the entire string. And then that would make it a n squared solution, so that wouldn't be too slow. So the way you can do this, and I think I've done this in other problems, is you can just maintain a prefix sum for both the left and the right for like all of your letters originally of all the character counts. And so then what you can do, like you would just have a prefix sum, so I can kind of walk through a few of them, and then you can figure it out for the rest of it. So let's say I have some characters here. So I'm going to initialize it with an index of -1, and I use a dictionary. So empty dictionary here. Then this index will be 0, and we'll just have 1a in the dictionary. Then basically for every new index, you copy the old dictionary and you add the character you have. So we'll have like 1a, 1f, then we'll have like 1a, 1f, 1b, and so on, right? You just basically maintain a cumulative count of every single character. And then once you have that, you can just figure out like what's the count I actually need. So if I want to know this range for both, right, I need to check this range for the left and the right, and I need to make sure the characters are the same. So in order to do that, I need to get the prefix sum at this index minus the prefix sum at this index, which will give me this range of characters. And same thing on this top one. So I need to get the prefix sum at this index minus the prefix sum at this index. So the indices are exactly the same. And then basically I'm going to get like a dictionary of character counts. And then I just need to compare those two dictionaries and make sure that every single character is equal. And that will be O of 26. So this is basically constant time. So now that I do that, that kind of handles the character count part. But now we need the left part outside of the query to be completely equal to this part. And we also need the right part outside of the query to be completely equal here. They can't be like just the same character counts. They have to be exactly equal because we can't flip this. And so this part you can do in a few ways. And the way I did it, I'm going to explain it in a minute. You might think you can just do like, you can just start at the right and just keep track of like the longest palindromic sequence or something. And then just make sure like, let's say the longest palindromic sequence ends over here from the right. You can just check like, is that number in the range? Is that number in the range? And so on. But that doesn't really work because you're going to have to check things in the middle, and I'll show you later. So the way to check that strings, you basically have to check like, is this string exactly the same as this in O of 1 time? And the way to do this is you can actually use string hashing. And I actually got like a take home for TikTok that used something like this. It was like a practice problem. So basically the way it works is because we want to include our indices in our hash, and we want to include the actual character, and you want to make your hashing function something that like gives you a very high probability that your words are exactly the same and there isn't like a mismatch. So for example, let's say I have something like this. Let's say I have something like A, D, B. Let's say my hashing function would just like take the ASCII value of every character and like add it together, right? So that, or maybe like the, yeah, that, or like 0 index. So this would be like 1, 2, 1. This would be like 1, 4, 1, 2 or something. So that would be like a bad hashing function, right? Because it doesn't take into account the order of your characters. And it's very easy to see how you can get like two strings that shouldn't match to match. Now you might have another hashing function that's like take the ASCII value of your character, multiply by the index, and add it all together. That also isn't fantastic because you can see how that would also collide. And if, like let's say I have like 0, 1, 2, 0, 1, 2. If I just take like the ASCII value of my character and multiply by my index or something, right? Or yeah, something along those lines. It's very easy to have a collision because you can have like A and B here, and then you can have maybe like B and A here or something. I think that would actually yeah, something like that. You can try things out, but essentially it would be very easy for it to collide. So a good hashing function that I learned is you take the index, or actually, sorry, you take the ASCII value of your character. So you just like ORed your character, and then you multiply it by the index. Actually, you don't want to hit the index here. You want to have a prime number here. Ideally, you want to have a big prime number. I ended up using like 130 something, which passed, but then I actually made it go down to like 3 and then also passed. So take a prime number, ideally kind of large, and you power it to the index, right? So for example, if we are hashing this, we would take the ASCII value of A, so ORed of A, multiply it by our prime number. I think I ended up using like 131 originally, and then to the 7th. And that would be the hash of this character. And then essentially you can add all these up. So for this whole string, you would add all these up starting in the beginning. So it's kind of like a prefix sum as well, where you would say like whatever character here is, you know, you would say like A, the ASCII value of A times 131 to the 0 plus so on and so on, right? So for this location, you'd imagine basically you have a value at every single one of these indices that's like this, and then you do a prefix sum. Then what this allows you to do is you can get a prefix sum. Like if you want to compare if these two are equal, you can do a prefix sum. Now you basically have to figure out like the hash total here will be the hash total of this entire string. So if I want to get this substring, this is just like a prefix sum. So I want to get the prefix sum of this location minus the prefix sum of this location. That will give me the hash value of this whole chunk. Then you get the hash value of this whole chunk, hash value of this whole chunk, compare them. And like I said, if your hash function is pretty good, which the one I showed you is pretty good, you will, with very high probability, not have a collision where your strings are different, but they hash to the same thing. Like it's gonna be very rare for that to happen. So basically, you can use this hash function to, in O of 1, figure out if substrings are exactly identical, and we're always going to be comparing substrings at the same indices, right? So we're going to compare like this section to this section and so on. So that will allow us in O of 1 to get to check if this is equal to this, and to check if this is equal to this. So if that's all equal, then we're good, right? We satisfied all our constraints. Like the bigger one with the characters rearranged needs to equal the smaller one, which you just do a prefix sum to just make sure the character counts are the same. But then the sections that can't be flipped need to be exactly the same, and you can use that with the hashing function. Okay, so now we have that out of the way. Now we have a few more cases. So case number 2. No coverage at all. And let's actually copy this down. And this is why I said this is like a very tough problem in my opinion, because there's a lot of parts, and even if you know like you might know exactly how to do it, it's still a super pain to code. So okay, so let's look at the no coverage at all. So let's say okay, I don't know why this is okay. Let's copy this. All right, so let's say A is here, B is here, C is here, D is here. So what I mean by no coverage at all is these sections don't intersect at all, right? Then what you're going to want to do is for both sections, check prefixes. For all other sections, check hashes. So what I mean by that is, in order for this to be possible, this section and this section needs to have the exact same character counts, because we can rearrange this whole thing to make it look exactly like this. So as long as the character counts is the same, then that's doable. So we're just going to use our prefix sums here to get it, right? So prefix sums at this index minus prefix sums at this index, and same thing here, prefix sums at this index minus prefix sums at that index. So that will give us this part. Then that's taken care of. So maybe we can cross it out like this, let's say. If this is good, that's taken care of. Same thing here. Prefix sums here needs to equal prefix sums here. So once that's done, we cross that out. Now we have 3 sections left. We have this middle part, right? We have this like 4 So this is where you can use the hashing, and this is why I said you can't just like look at your longest palindrome from the left, longest palindrome from the right. Now there is another way to do it instead of hashing. There is like a way to just like you just compare characters and you see like what's the longest prefix at or what's the longest like equal count from any index. That is doable in O of 1, but you can do this with hashing also. So like I said, for this middle part, you do the hashing. You just check like is this hashing prefix the same? Is this hashing prefix the same? And is this hashing prefix the same? And if all three of those are the same, then this is true. So yeah, so that's how you do the no coverage at all. You're basically going to have the two query parts. Then you're going to have the outside. You might not have any outside, right? Like theoretically, obviously, like you can have a D that goes over here. Then you won't have like anything out here, but it's possible, right? So worst case scenario, you'll have like these two query parts that you do a prefix sum. Then you'll have this middle section that you do the hashing function on, right over here. Then this right side you do a hashing function on. Then this thing you do a hashing function on. And like I said, you pre-compute your entire hashing function beforehand, and I'll show that in the code. So if all of these are true, if these counts are the same, if these counts are the same, if these two things have the exact same hashing value, if these two things have the same hashing value, if these things have the same hashing value, then this is good. Now you have, in my opinion, kind of the trickiest one, and that's you do have coverage, but it's not complete. So we'll call this like overlap. And let's, yeah, I think what we're going to do is copy this and then get rid of some stuff. And I'll show the overlapping one. So this is the last possibility pretty much. And what I mean by this is, let's say A is here, B is here. There's kind of two ways for this, and I basically handled it into I just had like an if else for this. So there's C, and let's say D is here. So here you could see that this query is like this, and this query is like this. So none of these queries, none of these like A, B, or C, D covers each other completely, but they do overlap. And this is kind of tricky. So for this section, if you take a look, first of all, yeah, let's just write down the steps you need for this. So first, get a count of left and right letters for each query. Meaning, get a count of like this prefix sum, this whole range. So A to B, get that range of letters. Like, what are all the letters? What are all the counts? Get a count of C to D. Then, notice in this picture, I can change all these letters. But it's kind of tricky, right? Because I can't just like match the letters directly. But there is a section here that this B can't be changed. This B has to be a B. And this is going to happen for this kind of query all the time, right? Assuming A and B is to the left of C and D. And I'll show you the reverse. So if A and B is to the left of C and D, there's always going to be a section in this right one that can't change, that is going to overlap with A and B. And so this part right here, and I'll draw it in blue, this A and B range has to have all of the characters in this section here. And the section can vary, like, for example, it doesn't have to be like this. It can totally be like, let's say C is over here. Like, that would also be acceptable, right? So this would be like this, and this overlapping section would be over here. But regardless, this whole part can't change. And in order to make my A and B, when I switch the letters, in looking like this, I need all of these characters to be in here, right? So I'm going to write that down here. All of these chars need to be in the A to B prefix of like character counts, right? Like, I'm going to get this character count dictionary, and all of these have to be in here with like an equal count or more in order for this to happen. So what I can do is I can take my A to B, check for all these characters, and subtract all of them. So what's going to happen here is I'm going to get like my dictionary here. I'm going to check to make sure these all exist and their counts, and I'm going to subtract all of these counts from here. And when I do that, I will have a count of A to B minus this part. Now, similarly, for this C to D, there's going to be a section to the right where this part over here, where these can't be changed, but they have to be in here. They have to be in here. Like, I can swap this around to make this, but they have to be in here, right? All of these characters have to be in here. So we can do the same thing here. So do the same here, right? We take all the characters in C to D. We check, are all of these in here with a prefix, with like a prefix sum to get this range, and then we subtract them all from C to D. And so notice that this length, and this length, right? Like this green plus blue and this green plus blue on the bottom is exactly the same, right? So what we did was we took this and we subtracted this. And then we took this and we subtracted this. So what's going to be left over in A and B and C and D has to be exactly the same, right? Because if we subtract this and if we subtract this from the top, like we can make some variables here, right? So we'll just say like, let's see. We can call this like L1, L2, and then we can call this like the chunk or something, right? So we can call this like X and Y maybe. So originally, L1 plus X equals L2 plus Y, right? If you just take all these characters, all of their combined counts will be the same, right? Like this green and blue equals these two. So then what happened was I took L1 and I subtracted Y. So I'm going to say subtract Y. Then I also took L2 and I subtracted X. So now you could see that these X's cancel out. So this minus X and X cancel out. And these Y's cancel out. So now what you have left in these L1 and L2, their character counts have to be exactly the same after these subtractions, right? We check for these sections, and then we subtract those counts. Now these two have to have the same character counts after doing those subtractions. So those are the three things that's like the thing we need. So we can say L1 counts have to be L2 counts, right? That has to be true. And then also now that we like took into account this whole, we can get rid of these variables now. So now that we took into account like all of this green and blue, now we have the same thing left, right? We have this, we'll draw this into a different color. We might have a left side over here that we didn't check for, and we have a right side over here that we didn't check for. And so this is, once again, the same hash function thing, right? You just hash function these two, make sure they're the same, hash function these two, make sure they're the same. And so if all three of these things is true, then this is true. So we can write this down in steps. So we can say for A to B, check the characters that have to be in there and subtract them from A to B, right? And obviously if there's a character, like if there's a character in here that isn't in here, then we can just return false right away because it's never going to be possible. So, and then same for AC, or it's going to be CD. Then check to make sure character counts in A to B equal C to D. Then hash function for the rest. And so that will give you all of it, right? And if this is all true, then this overlapping thing works. And that's basically all of your queries. You will either have a completely covered or overlapping, which, like I said, is the hard thing, or you will have no coverage at all. Now, for this, there's another version of this. So I will quickly show you. So in this case, our A to B was to the left. Now there's another version where this A to B is to the right. So let's get rid of some stuff. Okay, so we can have basically the same thing, except our A to B will be to the right. So it'll look something like as an example, something like this might be one, right? Where A to B is now to the right. You can see like this part ends to the right of this one. and this one was to the left. And it's basically kind of similar. You just like the indices are a bit different, right? So the sections are a bit different. The sections now are this section here and this section here. This section needs to be in here. This section needs to be in here. And then you still have your two side parts. So I just put this in if statements because the indices are a bit different, but the logic is basically the same. So that's essentially what you need. That's everything that you need to do the queries. And let's look at the code, and it's a ton of code. So that's why, yeah, it's pretty tough to implement in my opinion. I think this is probably the most code I've ever written in a LeetCode problem. So, and I tried to like refactor too because it was like a huge mess. So you have a mod value, and yeah, the other thing I forgot about the hash function is when you add. So remember, I said it was board of the character times prime number to the index, and you keep adding these up. So you keep do this again for every single index. And this gets really big, right? Because you can have like, let's say your number is 131, your index is like 1,000,000. This is obviously going to be like way too big. So the other thing about the hash function is you mod it by a mod value, which I just use 10 to the 9 plus 7 like in every LeetCode problem. And you can just use a power to handle that, and I'll show you. Yeah, so this will actually keep the value small, so it's not like too big. Okay. So you take your string, you get the half of the string, and then like I said, you get the left and right half of the string. And I just the right half of the string is just the right half reversed, right? So if we have ABC, CBA, then the left will be this, and the right will be this reversed, so ABC. And in order for it to be a palindrome, the left and right have to be exactly the same. So, like I said, you can just take the character counts in the left and right. If they are unequal, then every query is false, because if the character count in the left and right aren't exactly the same, there's no way you could rearrange it to make the characters the same because you don't have the same counts. Okay, so let's go look at this hash function really quick. So it's going to be, it's pretty simple. Here it is. So the hash function at index, and I made it cover indices that are out of bounds. So I made it cover like -1 and indices to the right of the last index and so on. So I didn't have to worry about out of bounds cases. So basically, like I said, you just simply keep adding the ASCII value of your character times power. Like I said, I started using 131 originally, which passed, but then I tried smaller values, and actually with something like 3 it still passes. But you can have 131 here. I think if you actually want a hash function that's more reliable, you do want a bigger value. It's going to be more likely to not have collisions. So you can do something like this. You can just use a power function in Python, basically give it a base, an exponent. Exponent is just going to be the index, and then you give it a mod value, and that'll keep it small for you, so it kind of does all the work for you. And then you just mod it by mod at the end. And you store it. So like I said, this is basically a prefix sum of hash values for your string, and then if you want a substring, you just get the prefix of whatever you need. So let's go back. So like I said, I just call it to initialize it, so we'll have a left hash and a right hash, and a left and right prefix sum. And like I said, for the prefix sum, you basically just take the prefix sum at the old index, and you add the current character value. That's pretty much all you do. You just take the prefix sum to the old index, you add the count of the current letter, and you do that for the left and the right. And I also made an out of bounds prefix just so, you know, like if I had a character, I don't think I need this to be honest, but I think it's fine. So basically what would happen is if I had like ABC, I wanted to make sure that like if I did check at this index, this would be the same as this. So I don't think it's super necessary. Okay, and then we have a result for the queries. And so like I said, I converted C and D to what I want them to be in my right string, like I showed you before, right? So if I have like in the original string, if it's like this, if C is here and D is here, then remember this is going to be index 0 of my new word, and this is going to be index 1 of my new word. So I made C over here and D over here because the range is still the exact same thing. Like it doesn't really matter if this is C and this is D or the other way, as long as the range is the same thing. So I just converted them in my to make the other word. And then here's all of our cases, right? So we have one covers the other, which is this first one, right? So if we have some word like this, so the one covers the other is like this one. Let's see. Like let's say it's this on the top and then this on the bottom, something like this, right? One covers the other. I just figure out like what's the biggest one and then use that as that's the only one that I care about. So then you just check to make sure that the count of characters here is the same as here, and these hash functions are the same. So we can take a look at that. And I just made functions for all these. So here it is. So you just get like the smallest letter and the biggest letter to get the whole range, and then you check the hash function. So I guess I could talk about this briefly as well. So when you check the hash function for the prefix sum, for the left side, like if it's from a letter all the way to the start, that's just the value here for the hash function. But if you're doing the right side, like if you want the hash function for a substring like this, you basically do the hash function here minus the hash function here, or the hash prefix. And so that's what I did here. So if these aren't equal, return false, and then check the prefixes to make sure they're the same as well. Then, let's see. Yeah, so then we have the no overlap, which I showed earlier, right, where you have two queries that don't overlap at all. Then you're going to have a center section. You're going to have a left and right hash, and you're going to have the actual two parts of the query. So the no overlap is over here. And so I just made two intervals because it doesn't really matter like which way A, B, and C, D are because you're comparing the same indices. And then you just compare prefix sums for both of them to make sure they're the same. And then you compare the hash functions for all the other chunks, right? The middle, the left, and the right. So that part is that. And let's see. Yeah, then there's the overlap one, which, like I said, in my opinion, is the trickiest one. And it's kind of hard to figure out. So here's the overlap, and I have like a helper function. So you basically calculate the prefix sum of the entire left piece and the entire left piece. And I made a prefix difference function that just gives you, I think it's up here. Here it is. Yeah, so you just give it two dictionaries, and it will give you the difference of the dictionaries. And yeah, that's pretty much it. Because you're going to be doing like prefix differences. So anyway, for this process overlap, you have two cases, right? So C and D are to the left of A and B, or C and D are to the right of A and B. It's very similar code, just the actual indices you use are going to be different. And so we need to make sure that the changeable parts actually have enough, right? Like the green parts have this blue stuff in it, and if they do, then we can go on. So if there's not enough in there, we'll just return false. If there is, you have to make sure that the changeable parts are equal and the left and right are equal, right? So the left and right have to be equal, and this is where I did all this whole comparison, right? So the left and right remainder have to be equal, the left hash has to be equal, and the right hash has to be equal. And also, this is where I checked to make sure that for everything in the blue range, it was in the green. And then I just passed in the dictionary of like the thing I was updating. I passed in the dictionary of the green range, and I updated all the values. And then if some values were missing, like if there weren't enough values in there, I would just return false. So basically, all of these things have to be true, and if all these things true are good, then it's fine. And yeah, this basically was like a huge case. Like before this, I think this was like 30 lines of code. And then this was 30 lines of code that was pretty similar, so I just made a helper function there. And I think that is most of it. Yeah, so just process queries and finally return result. So like I said, I think this ended up being maybe without comments, it's probably like 120 lines of code. And then before, when it was super messy, it was like 150 or 160. And I think my previous LeetCode like longest problem was probably around 70. So this was like almost double, which is like insane. Okay, but yeah, so we can run this. And I think there aren't too many accepted solutions for this one. So this was kind of all over the place. I think if you use like a smaller prefix, if you use a smaller value for your hash function, it's a little bit faster. But let's see. Yeah, so this ends up being anywhere from, I think it actually, I was like watching football and coding this, and it took me like 2 hours. So it was quite a long time. So this goes anywhere from like 1200 ms to like 3000. Anyway, let's go through the actual runtime. So So we pre-compute the prefix sums, and pre-computing the prefix sums, because there's only 26 letters. That's just going to be, so let's just say n is the length of the string and q is like the length of the queries. So pre-computing prefix sums is going to be O of n. Pre-computing the hash values. So if you use a power, it's technically logarithmic. So if you do something to like the power of like 1,000,000, it's technically logarithmic. So maybe it's best to say it's like n log n or something. But people usually say for powers that they're of one time, but in reality they're not. To do a power like that power function, if you're your own custom power function, it's actually logarithmic. But we'll just say it's O of n because that's what most people do. So yeah, so to pre-compute hashes, to pre-compute prefix sums, that's all O of n. To split the string, all that, O of n. Make the counter also O of n. So now for our space, so essentially for our prefix sums, every prefix will have maximum 26 characters. Or actually, we'll do that. Not yet. We'll do the space in a bit later. So to process every query should actually be O of 1, because essentially we do a prefix sum. We do like a bunch of prefix sums, right? So if you go back and look at this picture, so to get like this prefix sum is O of 1, to get this prefix sum is O of 1, to get this difference is O of 1, because getting a difference from a dictionary of 26 characters and another dictionary of 26 characters is O of 1. Getting this like hash prefix is O of 1. This is O of 1. So basically, to process a query is roughly O of 1, or you could say O of 26 if you want to. So it's going to be something like n plus q, where we do have to process every query. So q queries, and like I said, for space, the prefix sums I'm just going to say is O of n, and the hashes is going to be O of n as well, because even though at every single character you can store 26 characters, it's only 26 characters. So you'll basically have 20 or n dictionaries that have maximum 26 characters, which are just, those are just gonna be O1 dictionaries. Yeah, so I think that's all of it. So definitely a long problem, and like I said, for this one, I think it's very good to try to code it yourself, because even if you know how it works, it's just like it's a super pain. So I think these are the problems that actually get you better at coding. Like there are some solutions where once you learn the solution, it's very easy, but this one, even if like you know the exact solution, it's still a pain to code. So definitely would recommend coding it. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. And a happy new year. It's gonna be New Year for me in a few hours, so yeah, and thanks for watching.